Section 9.8, Second row diatomic molecules. Just as we treated the bonding in hydrogen by using molecular orbital theory, we can consider the molecular orbital description of other diatomic molecules. Initially, we'll restrict our discussion to homeonuclear diatomic molecules, those composed of two identical atoms, of elements in the second row of the periodic table. As we'll see, the procedure for determining the distribution of electrons in these molecules closely follows to the one we used for hydrogen. Second row atoms have valence 2s and 2p orbitals, and we need to consider how they impact to form the molecular orbitals. The following rules summarize some of the guiding principles for the formation of molecular orbitals and for how they are populated by electrons. Number 1. The number of molecular orbitals formed equals the number of atomic orbitals combined. 2. Atomic orbitals combine most effectively with other atomic orbitals of similar energy. 3. The effectiveness of which two atomic orbitals combine is proportional to their overlap. That is, the overlap increases, the energy of the bonding molecular orbital is lowered, and the energy of the antibonding molecular orbital is raised. 4. Each molecular orbital can accommodate, at most, 2 electrons with their spins paired. 5. When molecular orbitals of the same energy are populated, 1 electron enters each orbital with the same spin before spin pairing occurs. Molecular orbitals for lithium and beryllium. Lithium, the first element of the second period, has a 1s2, 2s1 electron configuration. When lithium metal is heated above its boiling point, lithium molecules are found in the vapor phase. The Lewis structure for Li2 indicates an Li single bond. We'll now use molecular orbitals to describe its bonding in Li2. Because the 1s and 2s orbitals of Li are different in energy, we may assume that the 1s orbital on the one lithium atom interacts only with the 1s orbital of the other atom. Likewise, the 2s orbitals interact only with each other. The resulting energy level diagram is shown in figure 9.37. Notice that combining 4 atomic orbitals produces 4 molecular orbitals. The 1s orbital of the lithium combines to form a sigma 1s and a sigma star 1s bonding and antibonding molecular orbitals, as they did for hydrogen. The 2s orbitals interact with one another in exactly the same way, producing bonding to sigma 2s and antibonding sigma star 2s molecular orbitals. Because the 2s orbitals of the lithium extend farther from the nucleus than the 1s orbital, the 2s orbitals overlap more effectively. As a result, the energy separation between the sigma 2s and sigma star 2s orbitals is greater than that for the one based in molecular orbitals. The 1s orbitals of lithium are so much lower in energy than the 2s orbitals, however, that sigma star 1s antibonding orbital is still well below the sigma 2s bonding molecular orbital. Each lithium atom has 3 electrons, so 6 electrons must be placed in the molecular orbitals of lithium. As shown in figure 937, these electrons occupy the sigma 1s, the sigma star 1s, and the sigma 2s molecular orbitals, each with 2 electrons. There are 4 electrons in bonding orbitals and 2 antibonding orbitals, so the bond order equals 1/2 of 4 minus 2, which is 1. The molecule has a single bond in agreement with its Lewis structure. Because both the sigma 1s and the sigma star 1s molecular orbitals of lithium are completely filled, the 1s orbital contributes almost nothing to the bonding. The single bond in lithium is due essentially to the interaction of the valence 2s orbitals on the lithium atoms. This example illustrates the general rule that core electrons usually do not contribute significantly to bonding in molecule formation. The rule is equivalent to using only the valence electrons when drawing Lewis structures. Thus, we do not need to consider further the 1s orbitals while discussing the other second-row diatomic molecules. The molecular orbital description of beryllium follows readily from the energy level diagram of lithium. Each beryllium atom has 4 electrons, 1s2, 2s2, so we must place 8 electrons in the molecular orbitals. Thus, we completely fill in the sigma 1s, the sigma star 1s, sigma 2s, and the sigma star 2s molecular orbitals. We have an equal number of bonding and antibonding electrons, so the bond order equals 0. Consistent with this analysis, beryllium 2 does not exist. Electron configurations for boron through neon. So far, we have independently considered the molecular orbitals that result from s orbitals and from p orbitals. We can combine these results to construct an energy level diagram for homeonuclear diatomic molecules of elements boron through neon, all of which have valence 2s and 2p atomic orbitals. The following features of the diagram are notable. 1. The 2s atomic orbitals are lower in energy than the 2p atomic orbitals. Consequently, both of the molecular orbitals that result from the 2s orbitals, the bonding sigma 2s and the antibonding sigma star 2s, are lower in energy than the lowest energy molecular orbital derived from the 2p atomic orbitals. 2. The overlap of the 2pz orbitals is greater than that of the 2px and 2py orbitals. As a result, the bonding sigma 2p molecular orbital is lower in energy than the pi 2p molecular orbitals, and the antibonding sigma star 2p molecular orbital is higher in energy than the pi star 2p molecular orbital. Both the pi 2p and the pi star 2p molecular orbitals are doubly degenerate, that is, that there are two degenerate molecular orbitals of each type. Figure 9.43, energy level diagram for molecular orbitals of second row homeonuclear diatomic molecules. The diagram assumes no interaction between the 2s atomic orbital on the one atom and the 2p atomic orbitals on the other atom. An experiment shows that it only fits for oxygen, fluorine, and neon. Before we can add electrons to the energy level diagram in figure 943, we must consider one more effect. We have constructed the diagram assuming there is no interaction between the 2s orbital on one atom and the 2p orbitals on the other. In fact, such interactions can and do take place. Figure 944 shows an overlap of a 2s orbital on one of the atom with a 2pz orbital on the other. These interactions affect the energies of the sigma 2s and sigma 2p molecular orbitals in such a way that these molecular orbitals move farther apart in energy than the sigma 2s falling and the sigma 2p rising in energy. These 2s-2p interactions are strong enough that the energetic ordering of the molecular orbitals can be altered. For boron, carbon, and nitrogen, the sigma 2p molecular orbital is above the pi 2p molecular orbital in energy. For oxygen, fluorine, and neon, the sigma 2p molecular orbital is below the pi 2p molecular orbitals. Given the energy ordering of the molecular orbitals, it is a simple matter to determine the electron configurations for the second row diatomic molecules boron through neon. For example, the boron atom has 3 valence electrons. Remember that we're ignoring the inner shell 1s electrons. Thus, for boron, we must place 6 electrons in molecular orbitals. 4 of these electrons fully occupy the sigma 2s and sigma star 2s molecular orbitals, leading to no net bonding. The last 2 electrons we put in the pi 2p bonding molecular orbitals. 1 electron is put in the pi 2p molecular orbital and the other is put in the other pi 2p molecular orbital, with the 2 electrons having the same spin. Therefore, boron 2 has a bond order of 1. Each time we move one element to the right in the second row, 2 more electrons must be placed in the diagram. For example, on moving to carbon 2, we have 2 more electrons than boron 2, and these electrons are placed in the pi 2p molecular orbitals, completely filling them. The electron configuration and bond orders for the diatomic molecules boron 2 through neon 2 are given in figure 946. Figure 9.45, the effect of 2s-2p interactions. When the 2s and 2p orbitals interact, the sigma 2s molecular orbital falls in energy and the sigma 2p molecular orbital rises in energy. For oxygen, fluorine, and neon, the interaction is small and the sigma 2p molecular orbital remains below the pi 2p molecular orbital, as in figure 943. For boron, carbon, and nitrogen, the 2s-2p interaction is great enough that the sigma 2p molecular orbital rises above the pi 2p molecular orbital shown on the right. Electron configurations and molecular properties. The way a substance behaves in a magnetic field provides an important insight into the arrangement of its electrons. Molecules with one or more unpaired electrons are attracted into a magnetic field. The more unpaired electrons in a species, the stronger the force of attraction will be. This type of magnetic behavior is called paramagnetism. Substances with no unpaired electrons are weakly repelled from a magnetic field. This product is called diamagnetism. Diamagnetism is much weaker effect than paramagnetism. A straightforward method for measuring the magnetic properties of a substance, illustrated in Figure 947, involves weighing the substance in the presence and absence of a magnetic field. If the substance is paramagnetic, it will appear to weigh more in the magnetic field. If it's diamagnetic, it will appear to weigh less. The magnetic behaviors observed for the diatomic molecules of the second row elements agree with the electron configurations shown in 946. The electron configurations can also be related to the bond distances and bond enthalpies of the molecules. As bond orders increase, bond distances decrease and bond enthalpies increase. N2, for example, whose bond order is 3, has a short bond distance and a large bond enthalpy. The nitrogen molecule does not readily react with other substances to form nitrogen compounds. The high bond order of the molecule helps explain its exceptional stability. We should also note, however, that the molecules with the same bond orders do not have the same bond distances and bond enthalpies. Bond order is the only one factor influencing these properties. Other factors include the nuclear charges and the extent of orbital overlap. Bonding in the dioxygen molecule is especially interesting. Its Lewis structure shows a double bond and a complete pairing of electrons. The short oxygen-oxygen single bond with a distance of 1.21 angstroms and the relatively high bond enthalpy of 495 kilojoules per mole are in agreement with the presence of a double bond. However, the molecule contains two unpaired electrons. The paramagnetism of oxygen is demonstrated in Figure 948. Although the Lewis structure fails to account for the paramagnetism of oxygen, molecular orbital theory correctly predicts that two unpaired electrons are in the pi 2p orbital of the molecule. The molecular orbital description also correctly indicates the bond order of 2. Going from oxygen to fluorine, we add two more electrons, completely filling the pi star 2p molecular orbitals. Thus, fluorine 2 is expected to be diatomic and have a fluorine-fluorine single bond in accordance with its Lewis structure. Finally, the addition of two more electrons to make neon 2 fills all the bonding and antibonding molecular orbitals. Therefore, the bond order of neon 2 is 0, and the molecule is not expected to exist.